Let's discuss sequences next. A sequence is simply a list of numbers, a1, a2, a3, ... all the way to an. I do want to emphasize here, these are different than series. Series we'll be looking at a little bit later on. Series are the sums and differences of numbers, or essentially taking the numbers of a sequence and combining them through addition, subtraction, turning them into terms and not just standalone values. Here, sequences, we just have these discrete numbers, a1 through an. So, for example, we could have the sequence 1, 4, 9, 16, and we could have, it just keep going, go on forever and ever. And so what we notice here is that a lot of times with sequences, we can write these using some formula. There's some rule that can describe this. And so if we think about each of these terms, what's going on? Well, 1 is 1 squared, 4 is 2 squared, 9 is 3 squared, 16, 4 squared, so forth. So there is a rule that can describe our sequences. In this case, what we could do is we could say, if we're going to call this the sequence an, well, we could say an, the rule to generate the nth term would be n squared. This is the rule to generate the nth term. So if we had a sequence where we want to have all these terms, what we could do is we could express this using our notation with our curly brackets indicating that we have a set of numbers. So we'd have the set of numbers in the sequence where the set would be the number squared, and those numbers range from n equals 1 to infinity. This would describe the sequence above. So we're going to be looking for a lot of patterns in this section. We want to figure out, can we write a sequence using some rule? Can we find some rule to find the nth term of that sequence? Now I do want to point out that sequences are just functions. Sequences are functions. They take an input and generate an output. So for example, in this sequence that I've given, we said, the first number we have, 1 goes to 1, then we had 2 going to 4, then we had 3 going to 9, which is off my type, but up here, notice I'm not connecting these through lines though. I'm not connecting these. It would be wrong to say that this is my function. These things are not connected through lines. They are discrete points. We had this first point. We had this second point. We have discrete points. They are in no way connected, but they do form a function. There is an input, there is an output once we have that rule. So let's do a couple examples where we just practice finding a formula for the nth term. Find a formula for the nth term of the sequence. Let's do as our first example, sequence -1, 1, -1, 1, so forth. What we see is the signs continue to switch here. The value is obviously 1, but then what happens to that 1? The signs are switching. And so there's a few different ways we've seen to do this, but two very easy ways to do it. One is to take -1 and raise it to the nth power. Because we know that negatives raised to odd powers are negative, and negatives raised to even powers are positive. And so this will give us -1, +1, -1, +1. So if n is equal to 1, right here we'd have -1, perfect. If n is 2, -1 squared is 2, -1, 3 is -1. That would be a fine sequence. There are other ways to do this. So if we think about the sine and cosine function, they tend to bounce around -1 and +1. So for instance, if we were to use, say, the cosine function. Well, I'm going to start with an n here, and let's think about that. Well, cosine of n just starting at 1 is meaningless. I need this to be some sort of pi n, because cosine of pi or 2 pi or 3 pi or 4 pi, those are what give me the ones and the negative ones. Now, if I were to plug in n equals 1 in right here, n equals 1 gives me cosine of pi, which is actually equal to negative 1, perfect. And 2 pi would be equal to a positive 1, very good. 3 pi, so this one would work as well. We notice how I'm always checking that I am getting that first number right. Because if our pattern instead started at 1, negative 1, 1, negative 1, well then these wouldn't be right. These would be off by a negative, right? If we were to think about the an where our n is equal to 1, well, we would have started with negative 1, not positive 1. So the way we can fix that is by changing that n to an n plus 1, or an n minus 1 would have worked. Because then if we start out at that first number, it's really 1 plus 1, which is 2, we get to the positive 1, and that would work. For our cosine, kind of the same idea, cosine of pi n, cosine of pi is equal to a negative 1, so how could we fix that? We could say, well, let's take n plus 1, and that would be a fix. I had said we could have used sine as well. Sine's a little bit harder to do, but it's still possible. We could take sine of pi over 2, gives us a positive 1, so let's start at 3 pi over 2, and then from there we could add, well, no, let me leave it like that. Let me finish the formula before I go messing with it to make sure I have the signs right. So pi over 2 gives me a positive 1, and if I add pi n to that, well, now we would start at 3 pi over 2 and then go to 5 pi over 2, so that would work, that would be fine. So it's always a good idea, once you have that rule that you think should work, test the first few terms. You don't have to necessarily write it down and work it out, but in your head just plug in n equals 1, n equals 2, n equals 3, make sure you're getting that pattern correct. Let's take a look at another example. Let's do this time 1, negative 1/4, 1/9, negative 1 over 16, 1 over 25. And so hopefully you're already picking up on a few of the rules that we've used already. I see that those signs are alternating, so I can use a very similar trick to what we did here. What we notice about the denominators is there are those 1, 4, 9, 16, 25. Same thing we saw in that first example where they're just perfect squares. So I could write this as negative 1 to the n, but remember, negative 1 to the n would start at negative 1, so we need to use that plus 1 here. And then times, well then we'd have 1 over n to the, 1 over, yeah, that's right, n squared. So I said it's the same as that first example, not quite, because the first example there in the numerator, here they're in the denominator, but it's the same idea, 1 over n squared. We could have also moved that numerator, could have written it maybe a little bit more simply as negative 1 to the n plus 1 over n squared. That would also be fine. Either of these, absolutely fine. Let's do another one. Let's take the sequence 2, 6, 10, 14, 18. All right, so this one's a little different. We haven't seen this pattern yet, but let's look for the pattern. What I notice is each of these numbers increases by 4. And we're starting at 2, and from there we are increasing by 4. So we could do 2 plus 4n, because this would be, if we start with this one, we would have 2 plus 4 one time over, and then 2 plus 4 twice over, so that's looking all right. But if we wanted to start at 2 here, we would need to use an n minus 1, because now we are getting that pattern that starts out at the 2. Right? If we think about n is equal to 1, that very first number that we would get, that very first number before would have, if we didn't have that minus 1 there, would have been 2 plus 4, which is 6. So we need to back it up by 1. We need to say, really, I don't want to add anything at the start. So our A1 here now is equal to 2 plus 4 times 1 minus 1. That zeroes out, so we are getting that first number as a equals 2, which is what we wanted. So now this formula is correct. Our sequence numbers, the first number is always the A1, and so we need to consider that we need to be able to plug in 1 for n to get there. Let's take one last example. So this one I'm going to do 1 over 25, 8 over 125, let's do 27 over 625, so forth. So again, we need to figure out the pattern. If we look at the numerators, 1, 8, 27, those are perfect cubes. 1 cubed, 2 cubed, 3 cubed. If we look at the denominator, those are multiples of 5. We have 5 squared, 5 cubed, 5 to the fourth. And so here we'd have 5 to the n, but again, if we were to plug in a 1 here, we'd just have 5 squared. That's not enough. That's just 5, not 25. So we need to make it an n plus 1. So once we have that, that would work. Again, if we were to start with n equals 1, we would have our entire sequence. So that looks good. Now, if we look at these patterns, sometimes these patterns were growing. That was this example right here. These numbers are going to consistently grow and grow and grow. If we looked at examples like this one kind of bouncing between positives and negatives, but if we look at what's happening to those numbers, they're getting smaller and smaller. 1 a negative quarter, 1/9, negative 1/16, 1 over 25. These are headed to 0. And then something like this one's not going anywhere. It's going from -1, +1, -1, +1. It's never approaching anything. So we could have something that grows, something that shrinks, we could have something that doesn't do anything. And then the last example, that one is also shrinking. So what we would say about these are some of these sequences are converging while others are diverging. Let's formally define what it means for a sequence to be convergent. The sequence AN, so remember that AN indicating our sequence name, and then the brackets indicating we have the set of all those numbers, converges to the number L if, for all epsilon greater than 0, there exists an n in the integers such that the absolute value of an minus L less than epsilon is true when little n is greater than n. So as our sequence gets infinitely large, as we take those nth series, numbers in the sequence, if we were to subtract the L from those, that would be less than any number greater than 0, any real number greater than 0. This should look very similar to our definition of a limit. It's the same idea. If we're looking at convergence, we're looking at that idea of a limit. If no L exists, we say the sequence diverges. If AN converges to L, we write the limit as n goes to infinity of the AN is equal to L, because it is just a limit statement. That's all we're dealing with, a limit statement. Or we can write AN converges to L with that arrow. L is the limit of the sequence. So because it is just a function, and functions have limits, sequences can have limits. So again, if we think about something like number 16, that was, or sorry, the first one that we did, rather this one right here. Those numbers were never converging to anything. We were going from -1 to +1, -1 to +1. There is never a convergence. We should be seeing some sort of convergence. And that wasn't true in this one. They just keep bouncing back and forth. Versus this second one, we had 1, then we had -1/4, then we had a +1/9, then we had -1/16, 1/25. We can clearly see that we are, as the n's are going on forever and ever, we are driving that to within some epsilon range here. And so as our n's go to infinity, our epsilon is going to 0. And that is what we're looking to see. So the sequence, we can say the sequence A sub n diverges to infinity if for all m there exists an n such that for all little n greater than big N, an is greater than m. So when we're talking about divergence, we can diverge in a few different ways. Sometimes it just diverges, meaning it never approaches any one number, and that's exactly that first case. We can't say that that one was diverging to infinity because it's just going up, down, up, down, up, down. It's not going to infinity. Versus that third one that we did, we had 2, then we had 6, then we had 10, then we had 14, 18. As that thing goes up and up and up, it is just going off to infinity. That is our trend. Again, it's not a line. Remember, I put that arrow on there just to indicate a direction. It's not actually a line because they're not connected dots. They're discrete values, but those values are growing more and more and more. So we could say that that sequence diverges to infinity. Likewise, we can also say that a function diverges to negative infinity. Likewise, the sequence A sub n diverges to negative infinity if, for all, I'll call it little n this time, there exists a big N such that for all n greater than n, an is less than little n. And so it would be exactly the same as that second example, just would be looking at some negative values there. They're going down and down and down. We can apply many of the limit rules that we've already seen to sequences because these are just the same limits that we've been dealing with. We can apply a lot of the same rules. So let's define a theorem. Let an and bn be sequences of real values and the limit as n approaches infinity of an is equal to, I'll call it big A, just so we can keep them apart rather than using L1, L2. And the limit as n goes to infinity of bn is equal to big B, where A and B are just real numbers. Then, well, one of our first limit rules was the sum rule. If we see that we have the limit as n goes to infinity of an plus bn, we can break that up into two different limits, and that is just equal to a plus b. Likewise for the difference rule, we have the limit as n goes to infinity of an minus bn. We can break that up into two different limits and just say it's a minus b. If we have constant multiples, constant multiple rule, so the limit as n goes to infinity of c times an is equal to c times a, where c is just any real number, just a constant multiple. We have a product rule, which says if we have the limit as n goes to infinity of an times bn, well, we can break apart those limits and it's simply equal to a times b. We have a quotient rule, which says if we have the limit as n goes to infinity of an over bn, we can write that as a over b with the restriction that b is not equal to 0. That's the only one that we need that restriction for. Now, there is something a little different to note here. which is to say that just because AN and or BN does not converge, does not mean that AN plus BN, AN times BN, AN divided by BN doesn't converge. So if AN and BN converge, we are guaranteed their sum, their difference, their product, their quotient, all of those things have to also converge. By definition, has to be true. But if we have two series that do not converge, once we join them, they may actually converge. So just to give you an extremely easy example of where this would be true, let's say n is equal to 1, 2, 3, so forth. Clearly, that is diverging to infinity. Let's take Bn to be negative 1, negative 2, negative 3. Clearly, that is diverging to negative infinity. And so An plus Bn is equal to 1 minus 1, 2 minus 2, 3 minus 3, which is equal to 0, 0, 0. And clearly that just converges to 0 because all the values are 0. That's not to say that every single time we have a series converging to infinity and one to negative infinity that they will converge. That could be true for something like An is equal to 15, 100, 1 million. I got my comma in the wrong spot. And then Bn is equal to 1, 2, 3, 4, so forth. Well, clearly, if we do these fractions, we're going to have 14, 98, 900,000, 999,000, and 997. Let me make that comma smaller so we can tell it apart. And clearly that's still going to infinity. So those were both convergent series. I meant to make them negative, but same story. It doesn't matter if they're positive or negative. One's converging, one to infinity, one's converging to negative infinity. Still can be a convergent or divergent series. We don't have a guarantee there. What I'm saying is we can't assume just because An or Bn does not converge that their sums, their differences, or their quotients do not. Now, the one rule that we do know is that if we have a divergent series, the constant multiple rule will remain divergent. If An is divergent, Can is still divergent. It doesn't matter what that constant multiple is. Even if it's less than 1, it's just going to diverge at a slower rate. If it's greater than 1, it's going to diverge at a much faster rate. So that is the only one of those rules that we can say if we start with a divergent series, it is still divergent. Let's think about another theorem that we had with our limits, which is the Sandwich Theorem. So we're going to tack on Sandwich Theorem for sequences this time. It's going to look very similar. You can also hear this called the Squeeze Theorem, just like we did with limits. And it states the series An and Bn, or let An and Bn be sequences of real numbers if the sequence An is less than Bn, is less than some other sequence, we'll call it Cn, is true for n greater than n, where n is just some integer, and if the limit as n goes to infinity of An is equal to L, which is equal to the limit as n goes to infinity of Cn, then the limit as n goes to infinity of Bn has to also equal that L. And that makes sense. We talked about this with theorems, but if we have, we talked about this with our other functions, but because these sequences are just a function, we have a bunch of points kind of converging in, we have some other points kind of converging in, however they're getting there. Well, obviously that third sequence in between has to be convergent in some way as well. So that should seem pretty easy, just like it was true of our other functions. So an example of this, we could look at, say, sine n over n. So what happens to this thing? Well, if we start plugging in numbers, we can see that sine bounces between being positive and negative. N's continue to grow. So we could simplify this. We could say, well, we know that sine n is just really making it messy because it's bouncing positive and negative, positive and negative. So what we could say is, we know that sine is between -1 and 1. And notice it could be equal to. I should say it can be equal to. Notice here we needed a strict inequality. So what I could do is just say, well, if that's true, then sine is going to have to strictly be between -2 and 2. And so what that also means is that -2 over n is definitely going to be less than sine n over n, which is definitely less than 2 over n. So we've restricted our sine function to being between these other two functions, -2 over n and 2 over n. And we can also very easily find the limit as n goes to infinity of the -2 over n. That is simply equal to, that's going to 0, which is also true for the limit as n goes to infinity 2 over n. Therefore, using the Sandwich Theorem, sine n over n must be going to 0. So sine's not a real hard function to think about either, but if we ever get into a situation where we have a kind of messier object, in this case the sine, or something we just don't like to want to deal with, if we can restrict it to being between two other things, well then we can apply our Sandwich Theorem to figure out its limit, or what it's convergent to. So we'll get another theorem. The continuous function theorem. And because we're dealing with sequences, we're going to tack on 4 sequences. We're going to let the sequence an be a sequence. Real numbers. If that sequence, if an is convergent to L and f is continuous, at L, then the function applied to the sequence must be equal to the function at the limit value. So let's take as an example on this one. Show the log of n plus 1 over n converges to 0. Well, to do this, let's think of our rule. Our sequence is n plus 1 over n. That gives us the nth term of the sequence. The function clearly equal to the log of x. And so we need to start by thinking about what is this an converging to. That's what we want to know. And so clearly if n is going to infinity, because we have n plus 1 over n, they're increasing at the same rate. The plus 1 is just basically a rounding error, right? If this is if we start at 1, we'd have 2 over 1, which is 2. And if we go to 2, we'd have 2 over 2 plus 1, which is 3 over 2, 1.5. But then if we have something like 100, 101 over 100 is basically close. It's very close to 1. I shouldn't say it's basically 1. It's very, very close to 1. We have a million. Million plus 1 is 1,000,001 over a million. Now we're starting to be within 1 just by a few hundredths or a few thousandths of a decimal place. And so what we're seeing is that the AN is going to 1. So because our sequence has a limit value of 1, and because our function is continuous, log is continuous at that 1, we can take f of 1, and the log of 1 is equal to 0. And so because f of x equals log x is continuous at 1, which is equal to the limit of the sequence, n plus 1 over n, as n goes to infinity. Because that is true, then log of n plus 1 over n, that is approaching 0. The nice thing about doing these sequences is we've handled limits before. We've taken the limit of something like this before. So just to write that out a little bit more, if we were to take the limit of our AN as n goes to infinity, we're just taking the limit of this n plus 1 over n. We know how limits work. We've done plenty of these before. So that is really not a new skill. We're just now recognizing that these are a little different than a function. They're a sequence, but they're working the same exact way. So we're comfortable, or we should be comfortable working with limits. We're applying the limits in the same way we were before, just to these sequences. Let's discuss another theorem. Suppose f of x is a function and that the sequence AN is a sequence. I say sequence the second I put those brackets around it, but I'm just defining what it is a sequence of real numbers such that AN is equal to a function on n for all n greater than some initial starting function value. Then the limit as n goes to infinity of AN is equal to L if the limit as x goes to infinity of f of x is equal to L. So this formally gives us a way to tie together our traditional limits and sequences. This is exactly what I was just talking about. This formally ties together limits of sequences and functions. I just finished stating how if we had seen something like this limit before, we would have had x's in there, but we would know how to find that limit. I was making the claim that we could think about them in exactly the same way, and this is our basis for being allowed to do so. This theorem formally gives us the ability. Remember, we said that sequences are just functions. That is what they are at their heart. And so we can do everything that we can to a sequence that we can to a function. So when we see when we want to determine convergence of sequences, we are just thinking about them in terms of what does a function look like. I want to talk about one last type of sequence, and I do recommend that you guys get lots of practice looking at convergence and divergence, but I want to look at one last type of sequence, which is a recursive sequence. These are sequences that can be defined recursively by giving the initial value or term, or it may require terms. For calculating later values. So an example of this is something called the Fibonacci sequence. Fibonacci sequence is a famous sequence that comes up a lot of places in life, a lot of different places in nature and everyday life. And the way the sequence works is that A0 is defined as 1. A1 is defined as 1. And then later terms or later numbers in the sequence, later terms in the sequence, they are equal to the previous two terms added together. So to find A2, we would have to take A0, which is 1, and add it to A1, which is 1 as well. We get 2. A3 would be equal to A1, which was 1, plus A2, which we just found to be 2. We get 3. A4 would be equal to the previous two added together. We get 5. A5 would be equal to the previous two, which is equal to 8. And so it would just continue in the same pattern, but we had to have been given these first two terms. Because the formula told us add the two previous terms, we had to know the starting point. Not all sequences are like that. For instance, the very first sequence we defined was just let an equal n squared. So we knew that a1 was equal to 1 squared, a2 is equal to 2 squared, a3 was equal to 3 squared, and we could calculate each of those, right? Not a problem. But some sequences actually start off with a number that is defined, or a few terms that are defined, and then from there we are told what to do. Just for a few other terms, a few other definitions, I should say, to avoid the word term too much. Let's talk about what it means to be bounded. If the sequence an is bounded above and below an is a bounded sequence. Otherwise, an is said to be unbounded. And what do we mean by this? So we can clearly see if something diverges to infinity, that it is not bounded. So for instance, an is equal to n. We'd have a1 equals 1, a2 equals 2, and it just keeps growing and growing and growing. So this is not bounded in any sense. But we had the one example where our numbers were convergent into 0. And so this was, I think, our second example, where we had negative 1 to the n over n squared, I believe it was. And so we saw that we had I guess start off as a 1, and we had negative 1/4, positive 1/9, negative 1 over 25. So even though these numbers are bouncing around, we can see that they are bounded. We can clearly set some upper and lower bounds to constrain them. Even something like our negative 1 to the n is bounded, right? Because we had negative 1, then we had 1, negative 1, 1. So can we set upper and lower bounds for those and contain those values? Absolutely we can. So just because a sequence is bounded does not imply that it is convergent. Sequences that are bounded are not necessarily convergent. They may or may not be. Like the two examples above, the first one we saw was convergent. I meant to draw that converging in a little bit more. We saw those values were shrinking in both directions and they're converging in towards 0. The second one, however, was not convergent. What we can say is that if a sequence diverges to infinity or negative infinity, it cannot be bounded. A sequence, if it is bounded in one direction, we can say it's either non-increasing or non-decreasing. A sequence is non-decreasing if an is less than or equal to an plus 1, meaning the next term is always bigger. A sequence is non-increasing if an is always bigger than or equal to n plus 1. And so in both of these cases, we would have an upper or a lower bound, right? If it's non-decreasing, meaning it's strictly increasing, that means it has a lowest value. There is a lowest point that it has. If it's non-increasing, it would have a highest point, so it would be bounded above or below. If it is non-increasing and non-decreasing, that would mean it's constant, which is convergent and in turn bounded because it's just equal to one value. A sequence is monotonic if it is non-increasing or non-decreasing, meaning it only does one thing. It continues to increase or it continues to decrease. That is a monotonic sequence, like we can have a monotonic function. And so we'll end on one last theorem, the monotonic sequence theorem. If a sequence an is bounded and monotonic, it is convergent. So monotonic means strictly increasing or strictly decreasing. And if we also know that it's bounded, that means it has a lower and an upper bound. And so if it has that lower and upper bound, the only way that is possible is if they are converging on some single value. So I don't need to draw those going back down, but they're leveling out to a single point. Or here on the second one, we can see it's leveling off on the bottom. So clearly converging to that one value because it is bounded, has to be stuck between those two red lines. And because it's strictly increasing or strictly decreasing, then that means it has to be converging to that one single value, call it